All right, for 521, we're going to talk about the things we did in 511, 512, 513, and really talk about what a translation, what a reflection, what a rotation are. So we built our basic understanding. So key concepts for this, make sure you understand the quadrants. Y'all should know this from 8th grade. But some things that y'all may be not thinking about. X and Y are positive if you're in quadrant 1. Y'all should know that. X is negative, Y is positive in 2. X and Y are both negative in 3. And X and Y, X is positive and Y is negative in quadrant 4. A translation is described in the coordinate plane by the distance that each point is moved with respect to the X and Y axis. If we assign H to be the change in X and K to be the change in Y, then we can define a translation T such that T HK of the point XY is X plus H and Y plus K. So basically, if H and K are both positive, then that means you're going to shift that point right H units and up K units. All right. If they're negative, then you go left and down. It's kind of like a slope sort of deal. It's just a translation, it's just a shift. Okay. A reflection is an isometry in which a figure is moved along a line perpendicular to the line called the line of reflection. Unlike a translation, each point in the figure will move a distance determined by its distance to the line of reflection. In fact, each point on the pre-image will move twice the distance from the line of reflection along a line that is perpendicular to the line of reflection. Basically, if you think about it like this, think about it like a reflection is like a mirror. Okay, so B, what we would like to think about here is this distance right here is exactly the same as this distance over here, right? So that and that are equal. Just like the distance from A is the same as the distance to A prime. Right? Those two are equal. And then same thing for C. They're perpendicular to the line of reflection and they are congruent, right? Those two halves are congruent. So those are pretty straightforward and pretty easy. Now, there are some rules. There are some rules for reflections that you want to look at here. If it's a reflection through the x-axis, right? Reflection over the x-axis, then really all you have to do is take the points and change them by this rule. Basically, they stay in the exact same place except the y becomes negative. Okay? Why does that work? Because if you think about it, if you're going over the x-axis, you're going, let's say you have the point 2, 3, right? Let's say we have 2, 3, and I want to reflect that over the x-axis. I'm going from the first quadrant, flipping over the x-axis into the fourth quadrant, where the x value is positive and the y value is negative, right? So that means that my x is not going to change because I'm flipping directly up and down. So I'm still the same distance to the right from the y-axis. But my y value, instead of being 3 above the x-axis, will now be 3 below because it's the same distance on the other side of that line of reflection. Okay, so if you change it by this rule, which means you don't ever have to graph anything if you understand what a reflection over the x-axis looks like. Reflection over the y-axis is the exact opposite, right? The x part is what changes, not the y. It's for the exact same reason. If I reflect my point 2, 3 again, right, it would then become negative 2 because I flipped to the left over the y-axis. Okay, so think about that hard and carefully for a minute. A reflection over the x-axis changes your y to a negative. A reflection over the y-axis changes your x. So it changes the opposite one. So you got to think about that if you're going to try to memorize these rules. Or you could just graph it, and that's way easier to visualize and see what's happening. And then the last one, this line right here, the line R, Y equals X. Okay, if you can't read that, it says R, Y equals X. That's what this is. So think about this line. That is the most basic form of a linear function. It goes through 0, 0, and it has a slope of 1. Okay? So rise 1, up 1 over 1, up 1 over 1, up 1 over 1. Okay? So what we're talking about here is the line that does this. Okay? That's your y equals x line. So if we're reflecting over that, we're going to be reflecting, say the point was here. It's not a point. Say the point was here. It would reflect to here. Okay? It reflects over that line. So it doesn't reflect vertically or horizontally. It reflects a change in both. Now, the trick there is, if it's specifically y equals x, then all you have to do is swap your x and y values. Okay? All you do is swap your x's and y's. The y goes first and becomes the new x. The x goes last, becomes the new y. All right? So let's go on. A rotation is much more complicated. Okay? A rotation is an isometry where all points on the pre-image are moved along circular arcs determined by the center of rotation and the angle of rotation. A rotation may also be called a turn. This transformation can be more complex. I'll let you read all the rest of that. I want to point out that in your notes and in your Walsh practice, if it's not specifically told for you to go clockwise, they are assuming rules in the direction counterclockwise. So basically, they're always rotating from quadrant 1 to 2 to 3 to 4. They're following that rotation. So it's always counterclockwise. So if you're having a question of, is it clockwise, is it counterclockwise? The rules from the notes are going to be for counterclockwise. But we could and probably will develop some rules for clockwise rotation because it shouldn't be that much harder to do based on what we already know. So the figure below shows a 90-degree counterclockwise rotation around the point R. Okay, so they show you that. Okay, and obviously B moves the greatest distance. The point that is furthest from the center of rotation is the one that will travel the greatest distance. Yep, that's what we just talked about. All right, so depending on the point and angle of rotation, the function describing the rotation can be complex. Thus, we will consider the following counterclockwise rotations, which can be easily defined. A 90-degree rotation around the origin, 180-degree rotation, and 270. These are counterclockwise. Okay? These rules do not work if you're trying to go clockwise. They change. They're different. Okay, we can talk about how they're different in another video or in class sometime. But for now, we just want to focus on these counterclockwise. And in your Walsh practice, if it says a rotation of 90 degrees, it's talking about counterclockwise. So remember that. All right, so 90-degree rotation about the origin is given by this rule, right? You swap your x and y, and the y becomes negative. If it's 180 degrees, they stay the same, x and y, but both become negative. Basically, it moves to the from the first quadrant to the third quadrant, right? Because it's 180 degrees. It's half of the 360. And then the last one is you swap your x and y. If it's 270, swap x and y, but the x part becomes negative. Okay. See, these are a little more tricky to remember, and these only work for counterclockwise. They all change depending on if it's clockwise or not. So for rotations, you can try to memorize these rules, and some of you will be able to do that, and you'll be fine. However, in my opinion, it's much easier on a rotation to actually graph the original figure and then go from there. Okay? All right, so examples. I'm gonna stop the video here and then do all the examples in the second video.